Also, another longtime friend, Dr. Professor Uwe Vogel from the Fraunhofer IPMS. Uh, Actually, the third Fraunhofer Institute we had in this event, which is great. And so Uwe will detail the recent achievements at the Fraunhofer in the areas of microdisplays, including high pixel densities and efficient displays, and even transparent OLED microdisplays. So thank you. You have the floor.
Thank you, Ron, for kindly inviting me for this talk and also for introducing this talk already. So let's say for the sake of fully seeing the slides, I will switch off my camera now. So I'm with the Fraunhofer Institute for Photonic Microsystems IPMS in Dresden, Germany. And of course, this work is not just my own. So there are a few more colleagues involved in this. We are actually operating our microdisplay activities here at Fraunhofer IPMS mainly based on two competences. So first one is IC backplane design. So design of integrated circuitries on 8-inch or 12-inch foundry processes and wafers. And then we receive the wafers back from the foundry based on our design. And then we perform emissive front plane integration, mostly on OLED. We have also started looking a bit into micro LED. Okay, so this is just an overview of the general microdisplay technology approaches. So I will focus today on the emissive ones that are typically non-transparent, but Ron already mentioned, and the title of my talks also mentions that I will also show an approach towards transparent emissive displays, microdisplays, and I will focus on OLED and less on micro LED today, but I will also have an outlook onto this. I will not cover the reflective, transmissive, or scanning ones like the LBS that we have just heard in the previous talk. What is important or interesting about the emissive approaches is that the light source is actually the same as the image modulator, whereas in the non-emissive approaches, you always need separate devices for the light source as well as the image modulator, and that typically already increases the form factor. I will not go into too many details on the differences of AR versus VR. Specifically for near-to-eye displays, of course, you have the options of being fully immersive, optical see-through, or also follow a look-around approach. I mean, probably most of you have already seen such sort of devices. And in addition, there's also, let's say, the approach of not really near to eye, but also with respect to the specification similar to optical see-through of head-up displays used in automotive or avionics. And there are a few major differences with respect to performance parameters or major performance parameters in between these different approaches. So specifically for fully immersive, so VR, you always rely on very high number of pixels, and that typically also translates into very high pixel densities as well as high frame rates. Whereas in optical see-through as well as head-up displays, very high luminance is required, and specifically in such look-around applications, also Google Glass was actually a look-around, although it was also a kind of a see-through prism, but people already actually looked underneath, or the regular field of view was underneath these optics. There you typically need very low power consumption because these are truly wearable devices where you need long battery life without recharging and so on. Okay, so lowest power consumption, that actually starts with the pixel cell architecture. And there's indeed already a difference between OLED and micro LED, since OLEDs are typically driven at about 2.5 up to 7 volts. Let's say if you have a single unit, for instance, in VR applications, a single OLED unit is sufficient, and that is definitely on the low end here. But if for optical see-through, very high luminance is required, therefore typically multi-units or stacked units are used, then you can go up to 5 volt or even more. So that's a bit, or let's say for micro LED, even for high luminances, that's typically in the range of 2 to 4 volt. But the major difference